the 10 gives you a 14, and the 17 gives you a 21, okay? So one force and coin can only be used once, and so you will get all those. But anything in the previous row you can copy down, and you'll get those copied over, and it'll look like the following. So you'll have a few more zeros now because of that. Now let's go down to the next row. We now have an extra 7-cent coin. And what will happen is this 0 will give rise to a 7, this 4 will give rise to 11, the 7 will give you a 14, and so on and so forth. And so you get 7, 11, 14, 17, etc., etc. And then you can also copy the zeros from the previous row, and so you'll get a whole bunch there. And then you can do the same thing with the last row, and you'll soon find out that for column 23, you're not going to get a 0. And that's how the answer for this particular question turns out to be no. So you cannot make exact change for 23 if you have limited kinds of as shown on this slide. Did this make sense?
Yeah.
All good? Okay. So we've gone from a version of the problem where we had unlimited copies of a certain coin to a version where we only have a limited number of copies of a certain coin, and then we would have to do this a little more carefully than before. By the way, we could have just combined the rows for the 2 10s and the 2 7s and make this easier, but you end up working a little bit harder for that. So the calculations become a little more complicated. Now, by the way, whatever we did here can be easily turned into an algorithm. And in order to write that algorithm, we're first going to write down some formulae which will tell you how an entry in the table can be filled. So if you look at row R and column B, and if we call this whole matrix as matrix C, what this says is that CRB in row R and in column B, the entry is 0 only if you can make exact change of amount B, and it's possible with the first R coins. Remember, for the Rth row, you can take all the first R coins that you have, and if you can make that exact change, then you can put in a 0 there. Otherwise, you can put in whatever other symbol you want. You can put in an infinity or an X or whatever it is that you choose. It doesn't matter. So in other words, CRB, the entry in row R and column B is 0 if whatever is, if it's a 0 in the previous row of the same column, or if it is a 0 in the previous row, but a bunch of columns to the left, that's off by exactly the denomination that you're looking at. And so it's either going to be CR minus 1B or CR minus 1B minus XR. Here, XR is the denomination of the coin in the Rth row. Remember, we had 10 and 7 and 4 and 7 and 10. Those are your XR values. And so this formula tells you exactly how to fill up the matrix at any given entry. And it doesn't tell you how to fill up the first row. So the first row, we have to do this by hand. And remember, for the first row, it's going to be a 0 either for the column for 0 or the column for x1, where x1 is the denomination of the first column. And since there's only one copy, you will only get 2 zeros in the first row, and that's in column 0 and column x1. And if you recall, we did that, our first row was denomination 10, and so we had a 0 in the 0th column and the 10th column. So this formula is very, very simple. You can easily turn this into Python code or Java code and fill up the whole matrix. And then all you have to do is to check whether the entry for the specific column you're interested in is a 0 or not. By the way, there is a problem in VJudge called subset sum, and make sure that you're given this problem for your Sunday session, for your mock competition. And this problem is actually quite simple. It's worded in the following manner. It says that if you're given a set of non-negative integers and a value s, your job is to determine if some subset of the numbers add up to s. If you think about this for a couple of minutes, this is exactly the problem, the exact change problem. And for instance, for our particular example, we were given three numbers, 10, 7, and 4, which were the denominations of the coins that we used. And we were asked the question whether we can attain value 43 with these three numbers. And so this is these two problems are essentially the same, and we can write code similar to what we did on the previous slide. So we're now going to look at a slightly different problem, which also has a very similar flavor. These are called packing problems or knapsack problems. For these packing problems, the idea is that you're given a bunch of items, and each item has a different weight. In this case, we'll assume that the weights of the items are x1, x2, up to xn. And we're asked the question whether we can fill up a box of capacity S with these items or not. In particular, the knapsack question asks whether how we can minimize the wasted space. So if you're thinking about it, this is exactly the problem we solved before, but with coins. The only difference here is instead of coins, here you have items of certain weights, and you're given a certain capacity of a box, and you're asked whether you can fill up this box to capacity. If you can fill it up, then the wasted space is 0. Otherwise, the wasted space is non-zero, and we have to figure this out. So the way we solve this problem is exactly how we solved the previous problem as well. Are there any questions?
Yeah, I have a question.
Yeah, go ahead.
Why wouldn't a greedy algorithm work for this one?
Not algorithm one, but the second one with limited number of coins.
He asked if why doesn't greedy work here?
Why doesn't greedy work here? Oh, I see. I didn't quite hear that. So greedy doesn't work because, well, you can try it with simple examples and convince yourself. Because greedy will choose the items in a certain order, and greedy algorithm is not allowed to sort of go back and fix things. So if you make a poor choice, then it doesn't know how to fix the problem. So for instance, let's say that you're asked to fill, let's say, a box of size 10, and you have 3 items of size 5, 5, and 3. Now, if you take the 5 and 5 together, you'll fill up the box of size 10. But if you take the item of size 3, and if you're committed to it, then you won't be able to fill up the box with the remaining items of size 5. So you're going to end up with wasted space. Greedy algorithms are of the kind where you make a decision on which item to add, and you cannot backtrack that. You cannot undo it. Otherwise, if you're allowed to undo it, it's not really called a greedy algorithm. I don't know. Did that make sense?
Yes, thank you.
Okay. So, as I was saying before, this packing problem is exactly the same as the coin exact change problem, and here we would use the same formulae as before. Instead of calling it exact change, I'm going to call it exact packing. And instead of R coins, we're going to use R items. So either we're going to put a 0 or we're going to put an infinity. If it's exact packing, we're going to put 0. If it's not, if you cannot pack it to the exact, then we'll put some other symbol to indicate that it's not going to work out for us. And we'll see that the formulae is exactly the same in the sense that CRB is going to be 0 if there is a 0 in the previous row but the same column, or if there is a 0 in the previous row but in a column that will allow for the last item to fill up the remainder of the space. So we'll do this for every column. So we'll do this for every possible box size, and then the column that we want will tell us what the answer is. And so essentially it turns out to be the same problem as before. The formula doesn't change. The recurrent, these are called recurrence relations. These recurrence relations also do not change. So that brings us to a last problem that's different from before. Before I talk about this, are there any questions on what we covered already? Okay, if there are no questions, then we are now ready to do a different version of the knapsack problem, or the packing problem. Here we are asked the question, what is the worst packing we can do? So instead of asking what's the best packing we can do and have minimum wastage of space, now we want to ask the question, what is the worst packing we can do? Well, before we talk about this, remember this problem we talked about the best possible packing by minimizing the wasted space. How can we figure out how much space is going to be wasted over here? Does anyone have any suggestions on how we could address this problem? Where remember, if we can fill it exactly, then the wastage is 0. But if we cannot fill it exactly, then there is going to be some wasted space, and we'd like to know how much is that wasted space for a given amount S. How would I solve this problem?
You go to the last row and check how many empty indices are at the most right side of the last row.
That's right. So if let's say we have a box of size S, we would see if this item is a 0. If it is a 0, then we know it can be filled to capacity and the wastage is 0. But if your 0 is over here, then how much is the wasted space? If this entry is not a 0, but the previous entry here on the same row is a 0, then it means that your wastage is going to be 1 because you can achieve S minus 1 here, right? So wastage would be 1 if this entry is a 0, but if this entry is also not a 0, if you have a 0 over here, then the wastage would be 2. If the last 0 is here, the wastage would be 3, and so on and so forth. So you keep walking across in the last row, figure out where the last 0 is, and that will tell you your wasted space. Does that make sense? All good? Okay. So now that we know how to solve the problem of minimizing the wasted space, how about we solve the problem of maximizing the wasted space? So we want to know what's the worst packing we can get. And over here, if the problem is not, if you're unclear about the problem, the idea is that you these are shopkeepers where they cheat you by saying that they don't have change. They'll give you some amount of coins back, and it won't make up to the exact change that they're supposed to give you back. And a lot of it is the skill in figuring out how to provide the coins in a certain order so that at the end, if you put in some other coin, it becomes over the amount, and so you end up settling for something smaller. So here the problem is you want to figure out what's the worst packing we can do for a given amount. And it turns out that we can modify what we did earlier for the worst packing, and it's a very similar looking formula. But before I write down things, I'd like to see if people have any ideas on how to approach this.
Professor, I have a question.
Yeah.
You're saying the worst packing. I'm confused on the definition because I mean the worst packing, you just don't choose anything, and that's the worst way.
Well, if you have a coin that can fill up the space, you should use it. So the worst packing is when whatever space is remaining, you cannot use any of the coins you have on here.
Oh, okay, that makes sense.
So if I have a 4-cent coin and a 7-cent coin and a 10-cent coin, and if I have to give you 3 cents back, then I'm going to give you a 0 because I cannot, I don't want to overpay you, and so I'll say I don't have it, I don't have right change. But what if I have to give you 6? Well, the best you can do is a 4. What if I have a 4 and a 7-cent coin and I'm supposed to give you 9 cents? 9 cents. If I give you a 4, then all the other coins are bigger than whatever is remaining, and so I can simply say that I don't have any better change there. Does that make sense?
Yeah.
How about the others? Any questions about what the problem is? Okay. So how should we approach this?
We could try finding the combination of coins that exceeds the amount, and then remove the biggest one of the two.
So what does it mean to find combinations? So one of the problems with all these knapsack type exact change type problems is that you cannot afford to try every possible combination. If there are n items, there are n factorial different combinations, and n factorial is exponential in n, and you just don't have the computation power to try every possible combination. So you have to come up with a different approach. This is why dynamic programming is so useful, because it does try many combinations without trying all the combinations. Okay. So do you want to refine your answer about how to check this?
So if we have the table, we find the first.
Go with the same table, okay.
In the last row, we find the first number that exceeds our number.
Okay.
and then after that we remove.
Then
the
where
largest
is
of
your
the
answer?
options. What's that?
So you're saying, I'm gonna have a table. The table, I don't know, looks like this, right?
Yeah.
And let's say, this is the amount I want, S. You're gonna look at the last row you said,
Right.
and and then what? So you're gonna look for you said you're gonna look for the first zero after S, is it?
Yes.
Okay, and then? So let's say this is S prime.
I guess I could try
What?
all of the numbers that are making
Sorry?
up we could try all of the numbers that are making up our column, and then subtract it from that number and see if it hits a 0.
Why should I go beyond S? I'm not quite clear about that part.
Well, if we hit, we have to give them the exact change, right?
That's not what I said.
Oh, that's what I
We never have to give, if you're the shopkeeper, you never have to give more than S. Okay?
Oh, okay.
So I think we should probably do an example. So let's say I have a 10, I have 2 7s, and a 4. Okay? So let's say that I want to return 12. So I could do, looks like the best I can do is 7 plus 4, right? That's the closest I can come. The amount of wastage would be 1. Is that clear? Because 10 plus 4 becomes 14, 10 plus 7 becomes 17, 7 plus 7 becomes 14, so 7 plus 4 is the only other possibility. Right? Now this is the one that minimizes the wastage. What would maximize the wastage? If I took 4, then that wouldn't be right, because I do own a 7-cent coin, which I can add and will still be under 12. So if I start with a 4, that won't work out well for me. What if I start with a 7? Then I still have a 4-cent coin, so I can add that 4, which means I'll still get 11. And instead, if I start with a 10-cent coin, then I can maximize my wastage because I cannot get any closer. So the worst packing is achieved when I use a 10-cent coin and the wastage is 2. Whereas the minimum wastage is 1. Did that make sense?
Yeah.
Or did I confuse you?
Yeah, that makes sense.
All right, now that you have a better understanding of this, what should we do?
I think one way to do it would be to, okay, so let's say we want to find number S,
Yeah.
and in the subset that I have, I find
Yeah.
the smallest number, I
Yeah.
subtract that from S, and then between that number that I achieved and S, if there is any number, the smallest number would maximize the waste.
Yeah. So, one possible approach could be to maybe sort the numbers, and so far when we looked at this table, we didn't worry about what order we threw in those numbers, right? We had a 10 followed by a 7, followed by another 10, followed by a 4, and so on, and it didn't matter earlier. now it seems that maybe it might matter. Maybe there is a certain order in which I should look at the coins. So should I go from smallest to largest? Should I go from largest to smallest if I want to maximize the wastage?
Largest to smallest?
Well, largest to smallest, remember, is typically what you would do if you want to minimize the wastage, right? If I ask you to pay me 28 cents, you would go with the biggest coin, let's say 25 cents, and then you would use 1 cent coins to make up the rest. So typically one starts with larger coins and gets as close as possible and then uses smaller coins to make up the rest. On the other hand, if you start with a smaller coin and if you're left with only large coins, then you can simply say, hey, I can't do any better. And you could end up with large waste. So large waste only happens if the remaining coins are large coins. Does that make sense? I mean, that didn't quite happen in this case here. In this case, it was the Bitcoin that gave us the worst wastage. But in general, it makes sense to use these smaller coins first. So if I were to do 4, 7, 7, and 10, then let's use 12. So let's go from 0 to 12. 0, 1, 2, 3. So our S is 12. If you use a 4-cent coin, then we know that we can do 0 or we can do 4, right? If you then allow a 7-cent coin, you could either do 0 plus 7 would give you 7, and 4 plus 7 would give you 11. And of course, you will also have these two here. If you use the second 7, you can do a 0 plus 7, that would be a 7. 4 plus 7, that would be 11. And then the rest would go up to 14, so it won't change anything. And then if you use a 10, you would get 0 plus 10, that would give you this guy here. Then 4 plus 10 would give you a 14. 7 plus 10 would give you a 17, and all of those are going beyond 12. And you're interested in this column here. So, how do I figure out the maximum waste over here, even though this entry is not a 0?
So what I just said, wouldn't that work?
Repeat it for me, please.
Yeah, so you wanna get the maximum waste. So you wanna, the number that you're looking for is 12 right now.
Yeah.
We're looking at. And the smallest coin that we have is 4. So
Yeah.
12 minus 4 equals 8. And then from 8, we look at the last column to see what is the closest 0 to 8. And in this case, it would be
7.
Yeah. No, from 8 to 12. So you would go up, you wouldn't look back.
I didn't quite follow that. So you want to look at column 8?
Yeah, let's say we mark column 8.
Okay.
And then we look at all the zeros from 8 to 12, from column 8 to 12, in all the rows.
Yeah.
And whichever zero is closest to 8, that's the answer.
Wouldn't it be closest to a number? 12?
Well, you're using 8 because 4 is the smallest coin?
Yeah, exactly.
Ah, okay. Yeah, any zeros before this doesn't make sense because you could have
Yeah.
added a 4.
Yeah, exactly.
But it's also possible that in order to achieve this number, you already added the 4, in which case 4 is not so critical.
Oh, yeah.
So it's a little bit tricky.
So what we're trying
Any
to,
other thoughts?
what we're trying to figure out is which is the first number with the largest distance from 12? Like the first,
You could say that, yeah.
yeah. I mean, we could start from 12 and then work backwards to the first zero, but that could be a lot.
Yeah, but in this case, you got lucky it's on the same row, but what if it's not on the same row?
Yeah, we have to check every row.
Well, you're going to run into the same problem that we had with the previous solution. You don't know how far to go.
Mhm.
Should I go to this zero?
So
No,
sorry.
you go.
So I didn't quite understand why what I said would cause a problem in some cases.
Right, well, in this case, it was easy because this zero did not add the 4. Okay, this you achieved only with the 10-cent coin.
Yeah.
Okay, and so therefore, it was okay not to go beyond 8. But if this had been achieved with the 4-cent coin somewhere, then it's not enough to go 4. You could go even further back.
Oh, yeah. Now I understand.
I mean, could we just store the largest zero in each row?
You
And then
could.
compare that to the final number? Like
Yeah,
subtract
yeah,
the final
you
number
could.
from the largest zero. Cause we do have to fill out the table, right?
Yeah, my concern is that even though you remember the last zero in each row, you don't know what things added in order to make up that particular amount. So what if that zero is very far away? Are you going to take that or not take that?
Well, it depends which one has the largest difference between the number and the last zero.
Okay, in this case, we looked at 12. What if I looked at 9? What's the maximum wastage?
It would be one of the cents, so
What is the maximum wastage?
2. Oh, no,
Everyone agree with that?
no, it's gonna be 3.
3. How do you get 3?
Sorry, 5.
You get 5 because I could use a 4 and then I can't top it with a 7. Right?
Yeah.
Now, how do I make that happen? So, I'm here, right? And how do I know I have to pick this and not this?
Because in the first row, it's a 4. So it'd be 9 minus 4, which is 5. That's the largest number. If you compare the other two, it's 5, 2, 2.
Yeah, we're going to run into lots of special cases here. because this 9 minus 4 worked because it's not bigger than 7, right?
So there's a better way.
Because the difference was smaller than 7, you couldn't use the 7-cent coin, right?
Well, I guess what I'm proposing is that the worst packing is always going to be the difference between the largest distance between the number and the next closest zero.
Not the next closest zero. You mean you actually wanted the farthest zero, right?
Of every row, like if you compare every row.
Oh, of every row. I
The
see.
difference between the number and the farthest zero of every row. The largest of those numbers. So in this case, it would be,
Okay, so if I took every row, then on the last row there is no zero. What do I do?
you ignore it.
Well, actually, the last row has a zero here,
Or actually,
a zero here, and a zero here as well. What do I do?
I think you just ignore it. Because you can't make,
How can I ignore it for 9 and not ignore it for 12?
because it exceeds our number. Oh, I see what you mean. So if it were empty to every single one, then we would have to go over. So there would be a special case.
So we are quickly running out of time. I'm going to show you some approach, but you guys will have to go and work on this a little bit more, okay? So I'm going to let me erase all of this here and show you something here. So we're going to sort the items in increasing order. And remember, earlier we were only writing zeros and we were not filling up the other entries. If for this version, we are actually going to fill up those entries as well. And starting from a 0, it'll start increasing 1, 2, 3, 4, 5, because that number will tell you the distance from the last 0, right? So in each row, if you see a 0, then after that it'll start to increase 1, 2, 3, 4, 5 until it again becomes 0, and in which case the numbers will start to reset and increase again. So when you look at these numbers for each row, you know exactly which one is the largest, and you can then use that. So the formula will turn out to be something like this. Either you use the and I think I made a mistake here. It shouldn't be minimum, it should be maximum. Either you take the value that you get in the previous row, or you find the one in the same row but in the previous column. Let me explain that with an example here. The idea would be something like this. So let's say that I'm filling up this table, and now I'm on this row. It's possible that there are more rows, it doesn't matter. And let's say that you filled up all these previous rows here, and you're now filling up this row. And let's say that you come up to somewhere here, and you want to fill up this particular entry. So this is row R and column B. So what I'm saying here is that if, let's say, the previous 0 was over here, the way we've done this, I'm going to call the next item as 1, the next one would be 2, 3, 4, and so this guy will simply be RB minus 1 plus 1. I forgot the plus 1 here as well. So I'm going to rewrite that formula for you, so give me a couple of minutes. So this one may simply be 1 more than the previous item here, or it will be the same as the item in the previous row, whichever is larger. So the correct formula is going to be, before I erase this, are there any questions of what I just said? No questions. So let's see. So this should have been RB minus 1 plus 1, and this should have been max. So what I'm saying here is that either you look at the same row previous item or the same, or the previous row, but where you're adding the XR, the coin denomination of the last item. Give this thing a try, and we can talk about this either on Sunday or the next Wednesday's meeting. I'm past time right now, so I need to stop. But if you want to, I'll send these slides over to Ricky, and you can take a look at this and see if this works for you. Okay? Any questions before we go? So don't forget to register for both ICPC and the North America qualifier, and don't forget to talk to people and form teams. I need to register the teams as quickly as possible, so please do that and inform Ricky about your team. Ricky, if you can get a chance, do talk to people and see if you can help them to form the teams. We need to get that done as quickly as possible.
Okay, sounds perfect. Thank you, Professor.
Okay, guys. Next week I'll see you in person, hopefully.
Recording stopped. Huh?
No. And so the intuition is that, and he skipped a lot of it, I don't know why, but he did this wrong. And it's like when, a while ago, it's like a year and a half ago. But it's like, if you take some subsets, right, for points, you wanna know, then there's the subset that you didn't take, and you wanna know the smallest one. So the smallest one that you basically skip is able to be added and not go over the limit,
No, long time.
then it's not a valid answer.
Well, you're sitting at 5 right now for an AI event.
So you wanna, for the knapsack, you wanna store for each capacity the maximum of
You go?
all the smallest possible coins that you can
Right
skip.
downstairs.
Perfect.
Like, if you can make a subset, you want to be able to maximize the smallest coin that you skip.
So I'll probably be researching it later.
Does that make sense?
Interesting. It was
I
like
understand
spread
the
out over
algorithm, I don't know what you're saying.
No, but how do you understand that? And, because I don't understand that. I don't know what you're saying.
Yeah, that makes sense.
Yeah.
How?
Because that's saying,
I left
hey,
all my stuff in the room
the
and it
previous
starts
one you were able to
at 5,
successfully
so
fill, right?
You can tell me
have a
how
gap
I-
between,
Alright.
increment all those gaps. So you know if you were to choose this coin, what is the gap from the previous zero?
or look at the previous coin denominator, minus the value of using that coin, and see
I
what
still want
gap
to
that is, and try to
have some team
maximize
building, I guess.
I guess maybe the sorting.
You know,
Yeah,
get
it's
everyone
fun,
to
right?
like know each other before we
Okay,
dive
I'm gonna
straight into
finish
the,
my
you know, good shit.
I still think it makes sense.
Coming?
Huh?
You coming?
Oh, yeah.
What are you going over?
We're just gonna have like a very like social discussion on AI and stuff. It should be fun, you know. You want to get philosophical, so we're
Oh,
gonna
yeah,
get
well, I'm
philosophical.
really super quiet.